So picture this. You're standing in your kitchen, getting ready to cook a complex dish.
Okay, I'm picturing it.
You don't just stand there completely still, thinking about the entire recipe for an hour.
Right, no, you'd burn something. Or starve.
Exactly. And you also don't just, start wildly throwing flour and eggs around without a plan. You interleave it. You think. You check the cupboard. You realize you're out of salt.
So you adjust the plan, maybe grab the soy sauce instead, and then you reach for it.
Yes. It's this constant loop of reasoning and acting. And I'm your host, by the way, welcoming you to today's deep dive.
And I'm thrilled to be here to help break this all down for you.
Because today's topic, it's honestly fascinating. We are diving into a landmark paper called ReAct, Synergizing Reasoning and Acting in Language Models.
This sounds super technical, I know.
It does, but our mission today is to show you how this paper is basically teaching large language models to act like that cook in the kitchen.
Combining their inner speech with actual, real-world interactions.
Right. We're talking about moving way beyond just predicting the next word. It's a cycle of thought, action, and observation. And the stakes are huge. We're looking at solving some of the most embarrassing problems in AI.
The pathological lying.
Yeah, hallucination and error propagation.
Mm-hmm.
So let's set the stage. What was the status quo before this ReAct paper dropped?
Well, you basically had two totally separate camps in AI research. They really didn't talk to each other much. You had the reasoning camp and you had the acting camp.
Let's start with reasoning. This is, what most of us are used to when we prompt an LLM. It's the chain of thought technique.
Right, chain of thought or code-to-DAC. Instead of just blurting out an answer, the model talks to itself, step by step.
It's that internal monologue. And, we have to give credit. Chain of thought was a massive breakthrough for math and logic.
Oh, absolutely. But it has a fatal flaw. It's a static black box.
Right. It's totally off from the world. It relies 100% on its internal memory.
And if that training data is old, or if it just doesn't know a fact, it doesn't stop and say, I don't know.
It just hallucinates. Confident.
Very confidently. The paper uses this really great example to prove it, involving an Apple remote.
Oh, right. The trivia question. They asked the model, aside from the Apple remote, what other device controls the program it was originally designed for?
Which is tricky. Most people wouldn't know that.
So the model tries to reason. It says, okay, Apple remote controls Apple TV. Apple TV is controlled by an iPhone, so iPhone.
The logic itself is totally sound. A equals B, B equals C.
But the premise is wrong.
Exactly. The remote wasn't originally designed for Apple TV. It was designed for an old Mac program called Front Row.
God, Front Row, I completely forgot about that.
Right, but the model hallucinated a totally plausible alternate reality because it couldn't actually go verify the fact.
Okay, so that's the reasoning camp. High intelligence, but isolated and prone to delusion. Then we have the acting camp.
Yeah, these are models designed to just do things. Action generation, navigating websites, playing text games.
But they don't have that inner monologue, do they?
No. Without reasoning, they're kind of like a robot vacuum just bumping into walls. They can't track high-level goals.
They can't handle exceptions, like the pepper shaker example in the paper. That one felt like watching a glitchy video game character.
It really is. The model is told to get a pepper shaker from a drawer. So it goes to the drawer, but the drawer happens to be closed.
And any rational person would just think, oh, it's closed, I'll open it.
But the acting-only model doesn't reason. It just maps the object to the destination. So it keeps trying to shove the pepper shaker through the solid wood of the closed drawer.
Just over and over again.
Entering an infinite loop of failure. Because it lacks the reasoning to track the state of the world.
Okay, so reasoning models hallucinate because they can't act, and acting models crash because they can't think. Enter the ReAct paradigm.
Yes. ReAct. Reason plus act.
And this isn't some crazy new hardware, right? It's a general paradigm, a way of prompting.
Exactly. It prompts the LLMs to generate both verbal reasoning traces and actions, interleaved together.
Break down that loop for us. What does it actually look like?
It's a specific trajectory, thought, then action, then observation, and back to thought.
So the thought helps the model track its plan.
Right. It induces a plan, handles exceptions, and decides what to do next. Then the action actually interfaces with external sources.
Like a Wikipedia API.
Yes. To gather ground truth information. And then it gets an observation back from the real world.
So going back to that Apple remote question, with ReAct, instead of guessing, the model thinks, I need to look up Apple remote.
It acts by searching Wikipedia, observes the text saying it was made for Front Row, and then thinks, okay, now I need to search for Front Row.
It grounds the AI. It actually checks its facts before answering. Which brings us to the HotpotQA and Fever experiments they ran.
Yes, these are knowledge-intensive tasks. HotpotQA involves multi-hop questions, where you have to connect multiple facts.
And Fever is fact verification. They gave the model a simple Wikipedia API, right?
Just 3 tools: search, lookup, which is like hitting Ctrl+F on a page, and finish.
So how did it do?
Well, ReAct significantly outperformed the acting-only models, and it was very competitive with chain of thought.
But there's a massive difference in trustworthiness, right? Let's talk about that hallucination stat, because this blew my mind.
It's the most crucial finding. They manually analyzed 500 examples where the models failed. For chain of thought, in its failure modes, it had a hallucination rate of 56%.
Over half the time it failed, it was just making things up.
Yes, but for ReAct, in its failure modes, the hallucination rate was 0%.
Zero. That is wild.
Because it was grounded in external documents. It didn't have to guess.
Now, in fairness, ReAct isn't perfect. We should mention the trade-offs.
Definitely. It does struggle sometimes with search result errors, like using the wrong keywords.
Or it gets stuck in a loop, endlessly searching, while chain of thought is more flexible, even if it's less factual.
Which is why the researchers came up with what they called the super solution.
Combining both.
Exactly. Combining internal and external knowledge. They used ReAct, but if it failed to find the information, it would fall back to chain of thought self-consistency.
Using its internal knowledge as a backup.
Right. Or, conversely, if the model's internal reasoning was highly confident and consistent, it would just use that. But if it was unsure, it would trigger ReAct to go verify.
That is so deeply human. If I know the answer, I just say it. If I'm shaky, I pull out my phone and Google it.
It's exactly that dynamic.
Okay, let's pivot to the decision-making tasks. Because answering trivia is one thing, but acting in an environment is another. They tested it on ALFWorld.
ALFWorld is a text-based game simulating a household environment.
So the prompt is something like, examine the paper under the desk lamp.
Right. And the challenge is that the agent has to navigate rooms, open drawers, find items. It requires serious common sense reasoning.
You have to know a lamp is probably on a desk, not in the refrigerator.
Exactly. And the results here were stunning. ReAct outperformed imitation learning and reinforcement learning methods.
The Bud-Eller baseline specifically right.
Yes. The best baseline had a 37% success rate. ReAct hit 71%.
Nearly double. Why did the ACT-only models fail so badly?
Because they couldn't decompose the goals. They just wander around. Whereas ReAct explicitly writes down its thoughts. It says, first I need to find the lamp, then I need to use it.
It makes a plan. And they also tested this in a shopping simulation, WebShop.
A very realistic one. Over 1 million products, incredibly noisy search results.
The task was something crazy specific, like find a 3-ounce bottle of citrus deodorant for sensitive skin under $50.
And you know how online shopping is. You get 50 results. Half of them are the wrong scent or the wrong size.
So how does ReAct have the advantage here?
It uses its thoughts to filter the options logically. It literally thinks, option A is 3 ounces but the wrong scent. Option B is the right scent. I will choose B.
It evaluates the features.
And because of that, ReAct outperformed imitation learning by an absolute 10% in success rate.
And it did that with just 1 or 2 examples in the prompt, right? Not massive training data.
Just a couple of examples. It's incredibly efficient.
I do want to quickly mention the inner monologue comparison, because AI talking to itself isn't totally new.
Right. They did an ablation study against the inner monologue method.
But inner monologue is rigid, isn't it? It's just restricted feedback.
Exactly. It just reacts to state changes. I am in the kitchen now.
Yeah.
But ReAct gives the model flexible reasoning. It lets the model decide what it actually needs to think about.
Which brings us to what might be my favorite part of the whole paper. Interpretability and having a human in the loop.
The why factor.
Yes. Because with ReAct, the model's decision process is completely transparent. We can read the thought right before it clicks a button.
Which is huge for debugging. You don't have to guess why the AI did something stupid.
Tell them about the keychain example. This perfectly illustrates it.
Okay, so the model is doing a task where it needs to find a keychain. It opens a drawer, and the keychain is right there.
Success. Task over.
You would think. But instead, the model hallucinates a weird constraint. Its internal thought tray says, I see the keychain, but I need to find the second keychain.
There is no second keychain.
Yeah, right. So it closes the drawer and wanders off to keep searching.
In a normal black box model, you just watch it walk away and have no idea why it failed.
Exactly. But here, the researchers saw the thought. So a human intervened.
Did they rewrite the code?
No. They literally just edited the text of the model's thought. They deleted the part about the second keychain and typed, "The keychain is likely in the drawer."
They just put the thought right into its head.
Yes. And immediately, the model corrected its behavior, grabbed the keychain, and solved the task.
That is profound. You're debugging AI behavior just by correcting its reasoning in plain English.
It completely changes how we interact with these systems.
It really does. Now, before we wrap up, we have to talk about fine-tuning and scaling. Because prompting is great, but training is where the power really unlocks.
It is. The researchers knew that giving examples in a prompt works, but they wanted to see what happens if you actually fine-tune a model on these ReAct trajectories.
And the insight here is a little disruptive to the current AI narrative, isn't it?
Oh, absolutely. They took a much smaller model, Polymer AB, and they fine-tuned it on the ReAct process.
And how did it do against the massive models?
It outperformed EP044.
A model literally orders of magnitude larger that was just being prompted. The small guy won.
The small guy won. Because you aren't just teaching the model facts. If you just teach facts, you promote memorization, which leads back to hallucination.
But with ReAct, you're teaching it a process.
You're teaching it how to reason and how to search. You're teaching it how to fish, basically.
That makes so much sense. So, to summarize all of this for you listening, ReAct is a bridge.
It perfectly connects the mind of the LLM, the reasoning with the body of the LLM, the acting and tool use.
It turns a static, sometimes delusional knowledge base into a dynamic, grounded agent.
And the big takeaway here is that this technology is moving us from AI that just talks to AI that actually does things reliably.
Because it's forced to show its work and check its facts against the real world.
It's a massive leap in trustworthiness.
It really is. Now, I want to leave you with a provocative thought to mull over. Think back to that keychain example, the thought editing.
The human intervening in the text.
Yeah. If we can control powerful AI agents simply by rewriting their internal monologue, literally putting thoughts into their digital heads, what does that mean for the future of programming?
It's a wild concept.
Is the future of coding just persuasive writing? Are we going to be arguing with our software to get it to work? Something to explore on your own. Thanks for joining us for this deep dive.
It's been a blast. See you next time.